Hello everyone, today we are doing section 4.3 complex plane, De Moivre's theorem. Let's recall, what are complex numbers? Complex numbers are numbers in the form x plus I, y. So actually number is a compound of two numbers. I here is imaginary unit and I square equals -1. So it's kind of a square root of -1. Usually, guys, we can graph complex numbers on a coordinate plane. Let's imagine that we do graph a real part of a complex number on x-axis and imaginary part on y-axis. Well, x and y can be just treated as x and y coordinates of a point. So I'm going to just kind of find x here, find y here, and there is going to be a point z, which is going to be a representation of this complex number. For example, z equals 2 plus 3i. So you see that x equals 2 here and y equals 3, so I'm going to measure 2 units here. Well, let me just take a different marker so we'll see this specific number, like 2 units here and 3 units on y-axis, so it's 3 here and 2 here, and my number z is going to come over here, the red. So this one is called real part, and this is called imaginary part. Normal numbers are also complex numbers. Like if you want to write down 2 as a complex number, you're going to write down 2 plus 0i, so no imaginary part. And we do have just imaginary numbers, like for example I, it's actually 0 plus 1i. Okay? Let's talk about magnitude of a complex number. Let me maybe erase this picture and one more. Magnitude of a complex number. Also known as modulus. How do we calculate magnitude? Well, that's how we write down magnitude, and then how do we calculate it? That's a square root of a real part of a complex number squared plus imaginary part of a complex number squared. For example, if z equals 3 plus 2i, the magnitude is going to be a square root of 3 squared plus 2 squared, which is going to be a square root of 13. So what is magnitude? What physically is magnitude of a number? If you graph a number, complex number, like 3 plus 2i, 1, 2, 3, 2 here, graph number z over here, 3 and 2. What is going to be actually this square root? Well, I'm going to connect origin with complex number z, and you see that the side 3 is going to make a side of a right triangle, side 2 is going to make another side of a right triangle, and here we actually see hypotenuse. So modulus or magnitude is actually distance from the origin to the complex number, so length of this segment. One more thing which we are kind of reviewing is a conjugate of a complex number. Well, I think I'll erase this again, maybe this. Yes. What is conjugate? Well, if you do have a number z, which is x plus iy, conjugate z with bar, in some books they put star, cap, but doesn't matter. Usually they're going to tell you how they denote conjugate. Is going to be the very same complex number, just instead of plus, we are going to have minus. And if you have minus here, there's going to be a plus here. What is interesting about conjugates? Let's multiply the number and the conjugate and see what is going to be the product. X plus iy, x minus iy, and we do remember the formula a plus b a minus b equals a square minus b square. I'm planning to use this formula because that's my a and that's my b, and that's my a minus b, right? So my a equals to x, so I'm going to have x squared here. My b equals iy, and I'm going to have iy squared. Well, for iy, I'm going to simplify it a little bit. So I'm going to square separately I and square separately y. So I square and y square. I'm going to recall that I square equals to -1. That was the definition of this I actually. So if this is -1, one more minus is going to give me a plus, and I'm going to have x squared plus y squared. Well, we can represent x squared plus y squared as a square root of x squared plus y squared squared, which is going to be what? This is modulus, and we are going to have actually new formula that if you multiply a number and a conjugate, you are going to have modulus or magnitude of a complex number squared. Well, just we are going to use it eventually, but for right now, just know this fact. Now, guys, we are going to learn how to represent complex numbers in polar form. Polar form. Well, what do we have? Right now we know Cartesian form. Cartesian form means that you have two numbers, x and y, which are just two Cartesian coordinates on xy plane. But we remember that every point can be also represented in polar form. So from x, y, we can move to r theta, right, to the polar coordinates of the very same point on the plane, if you treat z as a point on the plane. So let's see how it's going to work. We do remember from previous sections that r square is actually x squared plus y squared, the first set of formulas we covered in the previous section. And tangent of theta equals y over x, from where theta is tangent inverse of y over x. We do remember about addition of 180 rule because tangent inverse returns values from -π/2 to π/2, and if you have something greater than π/2 or smaller than -π/2, you will need to adjust actually the angle. Well, let's try to represent some complex number in polar form. So I'm going to consider example 1, and that's going to be complex number z equals square root of 3 minus I. Well, I was choosing this number because first, it's example for the book. Second, it's going to be easy to find the angle. So we're going to start with r. R is going to be a square root. Well, here is a square root. If you need to know r, forgot to write down the formula, it's going to be a square root of x squared plus y squared. So a square root, x squared, it's a square root of 3 squared, plus y squared. What do we have? -1 actually, the coefficient of I here. I'm going to square root of 3, which is going to give me just 3, and square of -1 is just 1, and I'm getting square root of 4, which is going to give me 2. Here, guys, we are going to use only one value for the square root, because here, square root is actually length, something what you measure with ruler. A ruler is never going to give you a negative number. Let's now calculate theta. Well, maybe I'll erase something from the top to finish calculations on this board and then kind of start new example, erasing everything. So for theta, we are going to have tangent of theta equals y over x, right? My y is -1, x is equal to square root of 3. We do remember that theta here is going to be tangent inverse of -1 over square root of 3. And generally speaking, it's supposed to be what? Well, that's a table value. Remember that we can take minus in front and have tangent inverse of 1 over square root of 3, which is going to give you minus pi over 6. Tangent inverse of 1 over square root of 3, it's our table value, right? Well, is it going to be actually my angle? Let's see where the point is going to sit, to which quadrant the point belongs. What you need to do, just grab the point. Square root of 3, x equals square root of 3, 1, 2, well, let's say square root of 3 is a little bit more than 1, but a little bit less than 2, so it's square root of 3 here. And -1 in y-axis is going to be somewhere here, and we are going to have a point here, so actually it belongs to 4th quadrant. Well, that's correct, so the value is correct. But for future, we will try to make theta something like a unique angle, and we are going to require that theta to be between 0 and 2 pi. We don't want to have like 10 millions of different representations for one complex number. Remember that for polar coordinates, there are many representations with different thetas. So we are going to require theta to be within 0, 2 pi interval. This one does not belong to this interval. So what we'll need to do, we'll need to add 2 pi to shift it into the interval. If I add 2 pi here, I'm going to get what? Well, 6 over here multiplies by 2, 12, minus 1, 11 pi over 6. And, well, that's going to give us some angle. Now I'm just going to graph the resulting value, and we actually converted my number to polar form. So in polar form, this number is going to be equal, in polar form, this number is going to have r equals 2 and theta equals 11 pi over 6. Okay? So now I'm going to graph the number, so you can, well, that's actually the graph of the number, so we can just label that the angle is 11 pi over 6, and the distance over here is 2 units. Okay? So we know how to kind of convert polar coordinate, Cartesian coordinates to polar coordinates. Now, usually people don't like to write down complex numbers in just like a polar form, like a coordinate. They want to show that it's a complex number. So how do we write it down as a complex number? Let me erase this example. We already kind of remember what were the numbers, right? Normal complex number look like this: x plus yi. We do remember that x is r cosine of theta, right? And y is r sine of theta. So we're going to use the r we found and write down 2, and cosine of theta, my theta is 11 pi over 6, right? Plus I, instead of y, I'm going to put r sine of theta, so it's 2 sine of 11 pi over 6. And that's going to be a better way to represent number in polar coordinates than this one, because this one is just the coordinates of a point. You see that r is going to appear in both coordinates, x and y, so we can always take it outside and have 2 outside and the cosine and sine numbers inside, plus I sine 11 pi over 6. Generally, any complex number can be represented in a polar form, and usually polar form is going to look like this: z equals length of r, right? We remember that this r, length of z, r is going to be a square root. This one is a square root of x squared plus y squared, which is actually modulus of z, right? And over here is going to be cosine of theta plus I sine of theta, where theta is going to be the angle of the number. So if you do have a number z somewhere here, you're going to have this and the angle theta. Okay? So if you do know how far away z is from the origin and you know the angle here, you're just going to plug them in here, and that's going to describe the very same complex number. Now the question is, why do we need two ways to represent complex numbers? Why don't we stick just to Cartesian way? Why do we need this more complicated polar coordinates? Well, actually more complicated polar coordinates are making it easier to calculate products, ratios, roots, and powers of complex numbers. Let me show you why. Okay, sorry. So I'm going to prove only theorem for products, but well, you just can kind of use formulas for the rest. So products. Imagine that you have two complex numbers in polar form. The first one is z1 r cosine of theta 1 plus I sine of theta 1, and z2 r2 cosine of theta 2 plus I sine of theta 2. I'm going to multiply them, z1 multiplied by z2, and I'm not going to do anything like different from normal multiplication. I'm just going to copy this number, put multiplication, and copy this number. So it's r1 cosine of theta 1 plus I sine of theta 1 multiplied by r2 cosine of theta 2 plus I sine of theta 2. What I'm going to do now, this is going to be a number, this is going to be a number, and I'm going to just put them as a product in front of the whole expression. These two parentheses can be multiplied using FOIL or whatever method, and I'm going to just multiply cosine by cosine and sine, and then this term by cosine and sine, okay? So cosine of theta 1 by cosine of theta 2, and then plus cosine of theta 1 by I sine of theta 2. It's going to be a long expression, so get ready to have two more terms. Now I'm multiplying sine by cosine, and the last one is going to be I sine of theta 1 by I sine of theta 2. I'm going to see that here I have I and I know that they combine into negative 1. What else I have? Well, I have two terms with just one I. So what I'm going to do, guys, I'm going to combine terms without I and with I separately. So this term does not have I, so it's a cosine of theta 1 by cosine of theta 2. This term is not going to have any I2 because two i's are going to combine into minus 1. So it's going to give me minus 1 sine of theta 1 sine of theta 2 plus, and because these two terms do have y, I'm going to take this I outside and have a cosine of theta 1 sine of theta 2 plus sine of theta 1 cosine of theta 2. Some people probably already remember the formulas which I'm planning to use here. Remember I was telling you, memorize one formula, and that formula for cosine over sum. So this is a formula, right? The cosine of theta 1 plus theta 2. Cosine minus sine. This is the formula for sine of the sum. That formula number 2 I was asking you to memorize, right? So this is going to be sine. Well, formula I'm supposed to write down theta 2 plus theta 1, but you understand, doesn't matter like how you place thetas here, theta 1, theta 2. So what I'm getting actually, it's R1 by R2 cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. You see that if we skip all this complicated trigonometry, to multiply two complex numbers, you will need to multiply the magnitudes, r's, and add the angles, which is kind of easy to do. I'm going to erase my proof and consider example of this multiplication. So I'm going to kind of one more time. To multiply z1 by z2, we'll need to multiply r1 by r2 and add theta 1 plus theta 2. That's going to be new r and that's going to be new theta. Well, let me see how it's going to work on example. Let's consider example, let's call it example 2. z1 equals 2 cosine of 30 degrees plus I sine of 30 degrees. z2 equals 5 cosine of 60 degrees plus I sine of 60 degrees. Somebody already converted my complex numbers into polar form, so I just need to multiply them. According to my new rule, the product of z1 by z2 is going to be product of r's, which is 2 by 5, and the sum of angles, so cosine of 30 degrees plus 60 degrees plus I sine of 30 degrees plus 60 degrees. I'm going to simplify a little bit this expression. 2 multiplied by 5 is 10. Here I'm going to have cosine of 90 degrees and I sine of 90 degrees. Everyone remember that cosine of 90 degrees is 0 and the sine of 90 degrees is 1. So if I multiply everything after that, I'm going to get my final answer, 10i. And that was not very difficult to do, right? For division, I'm not going to prove anything. I'm just going to give you the rule, division. If you have to divide two numbers, z1 over z2, well, by analogy, you can guess that if you multiply here, we are going to divide here. So divide the coefficients r1 over r2, and we are going to subtract thetas. Theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. Well, believe me or not, you're not gonna encounter division too many times. So that's why I'm not proving the formula. For multiplication, it's good. We are going to use it even in this lecture one more time. Okay, so no examples on division. I consider that you can do the same operations and just calculate what is going to be the result. But let's move to powers. Actually, we are going to mostly use this rule to calculate powers. And powers calculation is going to be called de Moivre's theorem. Who kind of published this? So powers. Let's consider that we have number z, and it looks like r cosine of theta plus I sine of theta. I want to calculate z square. What is z square? It's z multiplied by z, right? So I'll need to kind of multiply r by r, which is r square, and add theta to theta, because it's the same kind of number multiplied by itself. Sine of theta plus theta, which is going to give me, of course, r square cosine of 2 theta plus I sine of 2 theta. I want to emphasize 2 over here is going to match 2 over here and 2 over here. So we double the angle and we raise to the power of whatever power is the r. I'm going to do cube and then I'm going to do nth power. So for cube we can represent cube as a square by one more z, right? For square we already know the answer. So the answer is like r square cosine of 2 theta plus I sine of 2 theta multiplied by one more z multiplied by r cosine of theta plus I sine of theta. We remember that when we multiply numbers, we multiply r's, so we are going to get r cubed, and we add the angles. So cosine of 3 theta plus I sine of 3 theta, 2 theta plus 1. That's going to be my final answer. Again, number 3 here is going to match number 3 here and number 3 here. Now, general rule. Imagine that you did it n times. So if you do it n times, you are going to get a similar formula, r to the power of n cosine of n theta plus I sine of n theta. That's actually, this formula is called de Moivre's theorem. Well, let's see how the formula is going to work. Let's see, I think I'm going to erase everything from the board again because my example is not going to fit into this little space I have down there. And consider example. And guys, we are about half of the lecture done, which means that if you're tired already, you can take a break and watch the rest of it like next day. Maybe it's too much information for one day. If I was teaching this in class, I would do it in 2 classes actually. So, example number 1 on this de Moivre's theorem. Imagine that you have z, which is equal 3 cosine of 30 degrees plus I sine of 30 degrees. And you want to find z cubed. What is z cubed? Well, 3 cubed cosine of 30 degrees by 3 plus I sine of 30 degrees by 3. I'm going to simplify this a little bit. 3 cubed is 27, right? Cosine is going to be of 90 degrees and sine is going to be, of course, of the same 90 degrees. I do remember that this is 0 and this is 1, and my final answer is going to be 27i. Okay? Now, that was a really fake example. No one is going to give you actually polar form of the number. Usually you get Cartesian form of the number. So step number 1, you convert it into polar form, and step number 2, use the power theorem. And my example number 2 is going to be like more complicated now. Somebody wants to raise to the 5th power 1 plus I. So how do we do this? Step number 1, convert to polar form. Well, how do we do this? We remember that r equals a square root of 1, and the coefficient here is 1, so it's going to be a square root of 2. And a theta is going to be tangent inverse of 1 over 1, which is going to give us, well, tangent inverse of 1 is pi over 4. So the number actually is going to look like this. Square root of 2 cosine of pi over 4 plus I sine of pi over 4. And we'll need to raise it to the 5th power. Well, we remember that we put 5th power over here, so square root of 2 to the 5th power, and then we multiply by 2 the argument. So it's going to be cosine of 5 pi over 4 plus I sine of 5 pi over 4. Well, I think I'm going to calculate this and simplify, see what it's going to be. So when I multiply square root of 2 5 times, I'm going to have square root of 2 by square root of 2, which is going to give me 2. One more square root of 2 by square root of 2, another 2. And one more square root of 2, which does not combine with anything. So I have 4 square roots of 2. What is cosine of 5 pi over 4? If you draw a little circle over here, 5 pi over 4 is angle over here, right? Well, it's basically the same as cosine of pi over 4. Just remember that cosine is negative here, right? And sine is also negative here. So both of them are going to be negative. So I'm going to write down, so it's 1 over square root of 2 plus, minus 1 over square root of 2 plus negative 1 over square root of 2i. Well, I'm going to multiply everything, and square root of 2 is going to disappear, so it's minus 4 minus 4i. So that's a fifth power of this number. It doesn't look very similar to the number itself, right? Okay, so now guys, let's move to extracting roots. Well, we know how to do the powers. Let's learn how to extract roots. For roots, I'm just going to give you the formula. It's similar to powers, but just work in opposite direction, right? Remember that when we were doing powers, like third power or fifth power, we were raising actually r to the power of 3 or 5. Now, if you want to extract a root, you are going to extract a root. Here we were multiplying by 3, right? Now, if you want to extract a cubic root, you will divide by 3. So kind of doing opposite operation. Let's see how it works. So I'm going to write down roots. So we are extracting a square root of z. How it's going to work? Well, I'm going to write down the square root of r and the cosine of theta over 2 plus I sine of theta over 2. So basically I'm kind of doing all inverse to what I was doing when I was doing powers. Extracting a root, dividing by 2. Only one little feature for extracting roots, that actually when you extract a root, like a second root for example, you are kind of solving quadratic equation. Quadratic equation has two solutions, so you are supposed to have here two roots. If you write it down like this, you are just going to have one. So how do we get the second one? We are going to recall that theta is actually theta plus 2 pi n, right? So, and here we are going to add this 2 pi n and get possible different thetas from that. Let me write down general formula for extracting mth root of z. So it's mth root of r cosine here theta plus 2 pi n over m plus I sine theta plus 2 pi n over m. And here, how many n's you will need to consider to get all different values for thetas. Usually, if it's mth root, there are going to be m of them. Like for a second root, it's going to be just 2. Okay, example. First example, we are going to extract a cubic root of a certain number z, which is 27 cosine of pi over 2 plus I sine of pi over 2. Okay, this number is already in polar form, so it's not going to be that difficult. We don't need to convert it to polar form. So I'm going to extract a cubic root. Cubic root is going to be a cubic root of 27. And here I'm going to write down cosine pi over 2 plus 2 pi n divided over 3 plus I sine pi over 2 plus 2 pi n divided over 2. Remember that you don't need to calculate these two numbers separately, not over 2 or 3, because that's supposed to be the same angle. So you calculate only once. Here we know that's going to be 3. What are we going to get here? Well, theta 0 is going to be what? When you set up n equals to 0, you are going to get just pi over 2 divided over 3, which is pi over 6. Theta 1, you have n equals 1 here. N equals 1, it's 2 pi. 2 pi plus pi over 2 is going to give you 5 pi over 2, and over 3 is going to be 5 pi over 6. And the last one, theta 2, is going to be, you plug in 2 instead of n. 2 by 2 is 4, and pi over 2 is going to give me something like maybe 7 pi over 2. Let me double check it. 4, 8, no, not 7, 9 pi over 2, sorry. 9 pi over 2 divided by 2 and divided by 3 is going to be 9 pi over 6. So I got 3 different angles. Now I'm going to write down 3 different complex numbers which correspond to this cubic root. All I'll need to do, guys, I'll need to erase the formula. I'm hoping that everyone did copy the formula, already looked at the formula long enough to remember it. Well, again, you can always go back to the formula and look at it one more time. So Z0, I'm going to copy my R and then write down cosine. My first angle is pi over 6 plus I sine of pi over 6. My second number, I'm calling it Z1 just because it's n equals 1. 3 cosine of 5 pi over 6 plus I sine of 5 pi over 6. And my last one is Z2, 3 cosine of 9 pi over 6 plus I sine of 9 pi over 6. So there are 3 complex numbers. I'm not going to calculate numbers, though it's not difficult. The cosine of pi over 6, for example, equals the square root of 3 over 2, right? But I'm going to graph these 3 numbers to show you something interesting about this cubic root. You see that all of them are going to have same magnitude, which means that all 3 numbers are going to sit on a circle with radius 3. Now, the angle for the first number is pi over 6, something over here. So my first number, Z0, sits over here. That 5 pi over 6 sits over here. And 9 pi over 6, that's actually 3 pi over 2, right? 9 pi over 6, that's 3 pi over 2. And that's going to be sitting over here. Do you see that numbers are equally separated by angles? So angle over here and angle over here and angle over here are same. So a little trick to how to calculate the remaining angles. You calculate the angle number 1, which is just angle theta divided by number n. And then you divide 2 pi by number n, like 3, for example, or whatever you have here, and just add one more time to get all of them. Normally, number of roots is going to coincide with power or index of the root. Okay, now I'm going to ask you to do some extraction, and I'll need to erase everything. Remember my rule, you can stop video, do the work, and then compare your solution with mine. Well, I'm going to ask you to extract a very simple root. That's a fourth root of 1. Normally, guys, in normal algebra, in real numbers algebra, we are going to say that it equals to 1. But in complex number algebra, we are going to consider four different roots of 1. So I'm going to count to 5, and then I'm going to put solution on the board. So 1, 2, 3, 4, 5. Okay, how do we solve this? We start with converting number z, which is 1, into polar form. Into polar form is going to be very simple. R is equal to 1, right? And over here, cosine of 0 plus I sine of 0. How do I know? I did not do any calculations for theta. I just graphed 1 on the complex plane. It has only real part, right? 1. And I see that the distance here is 1 and the angle here is 0. So that's why I'm deciding to exist. Now, what are going to be the fourth root of z? According to my theory, it's going to be a fourth root of 1, which is still 1, right? Well, we can write down fourth root of 1, but this one is going to be just number 1. And then cosine of 0 plus 2 pi n divided over 4 plus I sine of 0 plus 2 pi n divided over 4. What I'm going to do? Well, I'm just going to see where these angles are going to be. So, because I'm going to have 4 separate roots, 0 is going to give me the root sitting over here, right? So I'll need to divide 2 pi into 4 equal parts and then kind of choose separation. 2 pi divided over 4 is pi over 2. So my next root is going to sit over here, my next root is going to sit over here, and my next root is going to sit over here. There are 4 roots. You can just put different ends like 0, 1, 2, and 3 here and just calculate the very same. I'm going to write down the numbers. Z0 is cosine, I'm not going to write down the fourth root of 1, a cosine of 0 plus I sine of 0, and because sine of 0 equals to 0, it's 1. z1 cosine of pi over 2 plus I sine of pi over 2, and the cosine of pi over 2 is 0, sine is 1, so it's I. z2 cosine of pi plus I sine of pi, this one is 0, this one is negative 1, so I have negative 1. And z3, my last number, it's cosine of 3 pi over 2 plus I sine of 3 pi over 2. And 3 pi over 2 is going to give me, again, over here 0, and over here I'm going to get negative 1, so minus I. So my four solutions are 1, negative 1, I, negative I. And if you look at my picture, they are exactly the numbers. So that's I, that's negative 1, and that's negative I. Okay, so we did all four rules. Last thing we are going to do in this lecture is to solve a couple of self-problems. And my suggestion is to try first to solve these problems without my help and then look at my solution. Okay, so I'm going to put the problems on the board. Well, you don't need to do the homework on this section in one day because it's a little too much. So self-problems. A. Square root of 3 plus I to the power of 6. Calculate. B. Cubic root of negative 8. Calculate. Okay, I'm going to count as usually to 5 and do the problems myself, and you compare the answers. So 1, 2, 3, 4, 5. I'm going to start with problem A. So you see number is not in polar form. I'm going to convert it into polar form. Square root of 3 plus I is going to be, well, first square this, that's going to be 3. Square this is 1. Square root of 4 is 2. So the r is equal to, what is going to be? Tangent of theta is 1, which is y, over square root of 3. We remember that this is what, pi over 6. So I'm going to write down cosine of pi over 6 plus I sine of pi over 6. Raising it to the power of 6 is going to give me z to the power of 6. I'll need to raise 2 to the power of 6. And the cosine pi over 6 multiplied by 6 plus I sine of pi over 6 multiplied by 6. I'm going to simplify this expression. 2 to the power of 6 is 64. Now cosine, 6 and 6 cancels. What is cosine of pi? It's actually negative 1, right? And the sine of pi is going to be 0. So my number is negative 64. And that's my final answer for question A. Question B. Question B is going to be longer. Abstraction of the root is always longer because how many roots are we going to have? 3. I'm erasing question A and moving to question B. So what is negative 8 in polar form? Well, again, when you convert something to polar form and you see something simple like negative 8, that's a real number, right? Sits on x-axis. You know the distance here is going to be 8 and the angle here is going to be pi. So I'm going to use cosine of pi plus I sine of pi. I'm cheating a little bit, but if you see this, it's not really like too bad. No one is going to complain. I'll need to extract a cubic root. So I remember that it's going to be 3 numbers, the cube of 8, and pi plus 2 pi n over 3. I'm going to write it down. Z cubic root is going to be 2 cubic root of 8, right? And the cosine of pi plus 2 pi n over 3 plus I sine of 2 pi n plus pi plus the angle you had over 3. Well, what we need to do, we just need to roll n through different like values 0, 1, 2, 3 and find the numbers. So let's set up n equals 0. We are going to have pi over 3. So my number z0 is 2 cosine of pi over 3 plus I sine of pi over 3, which is going to be what? We remember that cosine of pi over 3 is 1/2 and sine of pi over 3 is the square root of 3 over 2. We multiply everything by 2 and we get 1 plus square root of 3i. n equals 1, z1. So I have 1 here, it's 2 pi plus pi, 3 pi divided by 3, that's just pi, right? So it's 2 cosine of pi plus I sine of pi. Cosine of pi is negative 1, we remember, sine of pi is equal to 0, and I'm going to get just negative 2. n equals, 2z2, still 2, and I'll need to put 2 here. N is matching index of z. So 2 here, that's 4, plus 1 is 5. So cosine of 5 pi over 3 plus I sine of 5 pi over 3. Well, I just need to calculate what is going to be. Maybe, guys, you still remember how do we do this with numbers which are not from the table, right? 5 pi over 3 is going to be angle somewhere here. 5 pi over 3. It's almost 6 pi over 3, which is like 2 pi. So the angle is somewhere here. So what it's going to have, the cosine is going to be positive and sine is going to be negative. So it's 2, and this angle is pi over 3. So we're just going to have a cosine of pi over 3, which is 1 over 2, and the sine of pi over 3, which is negative, just because it's sitting over here. I by negative square root of 3 over 2. Let's multiply everything and get the number 2 multiplication of this minus square root of 3i. So I'm going to write down my final answer is going to be minus 2, 1 plus square root of 3i, and 1. How do I get 1? This one's supposed to be 1, I'm sorry. 1 minus square root of 3i. Okay. What I want to say, a couple of words, guys. Here we are extracting a cubic root out of real numbers. This one does not have any complex part. So what is going to be always true about this? First, you are going to get just a normal root. One of your roots is going to be just like normal algebraic root of negative 8, which is negative 2. That sits over here. All complex roots you are going to have are going to be conjugates. Conjugates means that one of them is going to have another one as a pair with minus. The reason is because when you multiply all of them, you're supposed to get 8, not supposed to get 8 plus something I. Well, this is just a checkpoint. You don't need to kind of do any work over here. Just like remember that. If you get, for example, here 1 minus square root of 2i, it's not going to be correct. These two numbers must be conjugates. Okay, well, do your homework, and that's all from this section. If it's too hard, watch it one more time. Don't try to do all the homework in one day. And ask me questions if you have. Thank you.